When we have something that we don't understand and we are asking it to do something and we can't get it to tell us why it's doing it and we can't see what it's going to do, that's just inherently a big red flag.
Welcome to Guardians of Alignment. My very first guest on this channel is Berick Cook, a fellow game developer who is creating AIRIS, a novel form of artificial intelligence. One of the most concerning aspects of machine learning, foundation of modern AI, loosely inspired by neurobiology, is that systems built with this approach are black boxes, meaning that their inner workings are unknown, even to their creators. So, if a future AI were to make a plan that would be catastrophically bad for humanity if carried out, we may not know until it's too late. In contrast, Berick has designed Iris to be transparent from the ground up. He hopes that one day Iris may be scaled up where it may serve as a supplement or alternative to machine learning. So I understand you're a game developer. Is that
Mhm.
as a professional or as a hobby? In what capacity?
It's just been hobby. So the game I've made a few games. I mean, I've like any game developer, I've made many projects that never saw the light of day. But I've made a few games. A couple of them were got one of them got fairly popular. It was called Pac-Man.exe. It was during the whole like .exe horror game craze, and I made a fun little Pac-Man game, and that was that. People still, I still see people playing it on YouTube, which is pretty cool because it was I made that back in like 2017, I think. Um, but all the games I've made, it's just been for fun. It's just been, I want to make a game. This is a cool idea. I want to see how this works, and made it and just toss it out there for free for anybody to play and download and stuff. So,
So this Pacman.exe, if someone wants to play it, where can they go to find it?
oh, that's a good question. Uh, it's berickcook.itch.io is probably the easiest way. It's also on Game Jolt, but it's a little harder to find on there. So,
All right, I'll make sure to put a link to that in the description on this video. We can
well, thank you.
later. How did you get into AI alignment?
So it started with getting interested in AI in general, of course. Some of my favorite movies growing up were all of the anything to do with robots. I mean, Star Wars, Star Trek, Data. You've got Terminator. You got all whole bunch of B movies, like even stuff like Robot Jocks with the giant robots and stuff like that. I just loved robots like that. I just loved that concept. And as I got into video game development, and I started wanting to make more complex video games, I was like, okay, how does AI work? Like, how do you make characters in video games? And so I was reading up on that, and I was like, okay, how do I do this? And it was like, daunting. There was so much information out there about like, the pathfinding algorithms and decision trees and all this kind of stuff. And I that was all completely new to me. And I was just like, I this is so much. This is crazy, all this kind of stuff. And I thought at the time, it'd be awesome if there was a way that you could just have like a plugin, right? You have a plugin that's this is my AI, and you drop the AI plugin. The AI looks at the game and says, "Oh, okay, this is what my character is supposed to do. Okay, this is what I do." Just like a drag and drop AI. And I thought that would be so cool. And it kind of tickled in my brain, and I got to thinking, well, how could you do that? Like, how is that possible? And then in 2004-ish, there was on a game development forum for Game Maker Studio, which is what I used for many many years. There was a forum thread, a very long and detailed forum thread about learning AI. Like, how do we make our AI in our characters more intelligent? How do we make it so that they react better, so that they're not so chunky, so that they're more lifelike? These are all the topics that were in this thread and talking about, how can we make more adaptive AI that reacts to the player and all that kind of stuff. And as I was going through and watching or interacting with this thread, I had this idea of, okay, you know, when we make AI and we teach it how to interact with the environment, we're coding it in. What if it could just learn what we're coding? We code in the rules. What if it could just learn the rules? That would be awesome. And that's as far as it went. Like, I had no detailed plan. I had no, that was just like that would be cool. That would be a cool thing. And then as time went on, I got to making games and doing other stuff, and I just kind of set that on the back burner in my head. But it was in in 2013 when DeepMind released that paper showing that they created deep neural network that could beat Atari games, right? It beat a bunch of Atari games. It didn't beat all of them, but it beat a pretty decent amount of them. And that was very impressive. Like that kind of shocked me back into thinking about this more because the the thought that we can now make a program that can learn an environment that it hasn't been explicitly programmed for. It can beat a video game that it hasn't been programmed for, right? That immediately went right back to 2004 in my head. I'm like, they did it. Here's this drag and drop AI. You toss it in and it can learn how to play your game. That's amazing. And I got to looking into it more and seeing, okay, how did they do it? What did they do, and how does these deep neural networks work, right? Because neural networks, isn't that like how the Terminator works? Like when that's what they talked about, like neural network, CPU, learning computer. And I was like, okay, that's cool, but like, okay, so if these things get more capable, like, I mean, we've made lots of movies about the robot apocalypse. What do we think about that? Like, are we taking on like Isaac Asimov's laws of robotics with this? Like, what are we doing? And so I started looking into it more, and I learned about like paperclip maximizer, concept, and Nick Bostrom's book, Super Intelligence, and it was really interesting to me that there were all of these. This problem went a lot deeper than like I thought, right? It wasn't just like, oh, we'll just tell the robots to be nice and they'll be nice. We'll just program them to be good and then they won't, rise up against us or whatever. And and so that really got me thinking more on the technical side of things, right? Thinking about, okay, so we have these AIs, they're getting smarter. They're not a problem now, but it's easy to see the trajectory of where they will become a problem. And how are we going to address that? And what is the consensus on this? And the consensus was we have no idea. Like that's basically, and it's still the consensus, right? Everybody's saying, we need to do this, but we don't know how yet. We're still trying to figure that out. And so that's really what got me focused, not so much on the development part of it at that point, but more on in around 2013 was when I was like, okay, the technical side of this, right? We need to think about a way that we can be careful with these things.
You're seeing computers and AI, in the past, and they're like, developing for a long time, and it doesn't really seem like a problem. But then something kind of changes in the way AI is built, and suddenly there's something like a little more worrisome about it. I heard you mentioned learning about neural networks as creating a sense of unease.
Mhm.
What, in your view, is kind of the essence of what makes existing AI seem like it might be dangerous as it gets scaled up?
The unknown, and it is, there's so much that we don't know about these systems in current machine learning and like the deep neural networks and large language models and all of these techniques, is that they're when they talk about them being a black box, they really mean they're a black box. It's not like something that we can crack open and see how this works. We feed inputs in, we get an output. And when we tell it, okay, that was a good output or a bad output, and it does some magic inside, and then the output gets a little better. And then we tell it yes, no, and then it does some magic and the output gets a little better. And we have a idea of how that of what's going on inside, but we don't know why or how, or especially as these things scale up, that the connections between all of these different neural nets and neural nodes and all that kind of stuff, it becomes very opaque. We don't know what's going on. And so when we have something that we don't understand, and we are asking it to do something, and we can't get it to tell us why it's doing it, and we can't see what it's going to do, that's just inherently a big red flag. And I think that that's the big difference between the AI that we have now and the AI of old is that the AI of old, we had all kinds of methods for debugging, right? We could see, okay, why is my character, or why is my little guard character running up against the wall? Why is he stuck? Or why is he just standing there and not paying attention to anything going on around? You know, and we can go into the code and be like, oh, okay, I see. This plus sign needs to be a minus sign, or whatever, and we could figure out. We have an idea of how those systems work. Even the large scale of the older AI, right? The good old fashioned AI had unexpected behaviors, right? You could that happens all the time in video games. There's glitches, and sometimes they're hilarious, sometimes they're really frustrating. And these are systems that we hand coded, we understand how they work, and they still break. And they still do weird things sometimes because they're just stuck in situations that we didn't anticipate it when we were coding it. But with machine learning, it's very much we don't know. We're throwing a whole bunch of hardware together, seeing that it can do something, and then throwing more hardware into it to make it do more things, and without understanding. And I don't see a way that we really can understand how it's doing what it's doing or why it's doing what it's doing. And those are two big questions that are huge in any kind of safety paradigm.
Yeah, and to clarify the audience on this black box nature of neural networks, we know the process by which neural networks get shaped, and we can actually look inside. But if you look in there, it's just a bunch of numbers, like floating point numbers that don't really mean anything in terms of anything that we care about. Like, it identifies this image as a cat. Is it looking at eyes or other things, or is it just kind of looking at random pixels? Like, anything meaningful is where our understanding breaks down. And there's some work on this field called interpretability, which tries to understand machine learning the way like neuroscience works, just kind of observationally, but that's very much in its infancy. So one other kind of foundational question I have here before we get into your project, which I definitely want to talk about,
Mhm.
uh, is there is this essay called The Bitter Lesson, which kind of explains uh, the triumph of machine learning over a lot of other methods of AI. So, in the past, like, machine learning hasn't been like the go-to for all time in AI.
Right.
There was a point where like lots of different approaches were being explored. Some of which were very much like traditional programming, where you could kind of follow what's happening. And then at some point, machine learning shot out ahead, and a lot of the other branches in AI kind of withered and died off. You mentioned the phrase good old fashioned AI, or GoFi is an acronym. It's actually kind of a somewhat a derogatory term for things outside of machine learning.
Yeah.
And so the core idea of the bitter lesson, I think by Richard Sutton, uh, was that at every stage of AI development, lots of people have tried to engineer knowledge into the system, and this ended up being negative value ultimately, just kind of leading people down false paths.
Hmm.
So, for example, with chess, people initially tried to create rules, and then even when we started having machine learning, they tried to engineer other ideas in, kind of trying to hope to guide and help the AI. But ultimately, when the systems really took off, it's when the engineers kind of stepped back, took their ideas out of the system, and just and focused on the search process rather than
Hmm.
trying to tell it the process. Um, so before we get into your approach and how you kind of get around this issue, what do you feel is kind of the essential challenge in good old fashioned AI kind of approaches that need to be overcome in order to match what ML is doing well?
Pretty much exactly what you just said. So the key is that we can't, we try and structure. I mean, there's been many good old fashioned AI approaches to something like machine learning, like you said, and a lot of those try and structure things and build things out and in okay, you have a concept and you have to attach these attributes to this concept, and there's a flow to it, and we try and engineer these types of things, and they just fail because it just explodes in complexity, and there's too many, edge cases and all of this kind of stuff. I think the real challenge, taking this from, and why I think machine learning has really exploded in comparison to good old fashioned AI, or one of the ways that good old fashioned AI is described as symbolic, right? It's symbolic AI. You have symbolic AI and you have sub-symbolic AI. And sub-symbolic AI, that's machine learning. That's what's considered machine learning. And symbolic AI, that's considered like good old fashioned AI. And what that means is that when you're doing symbolic programming, right, you're coming up, you're taking a high level concept and you're writing out an idea, like what you want the program to do on a high level. Like, there's high level programming languages. I mean, yes, you could technically code a program in machine code, right? Just raw binary zeros and ones and stuff like that. But I mean, good luck. It's going to take you a long time, right? We have many, many, many layers of abstraction that take and make it into a much more symbolic form for us to be able to say, if this, then this, and then it translates back down into the actual machine code instructions, the binary instructions to get whatever the process is done, right? So that's very symbolic. And the sub-symbolic, like when you're taking symbolic inputs, you're taking concepts, you're taking ideas, you're taking like a cat, right? You have a cat and you say, okay, this is a cat. That's a symbolic idea of this is a cat. And if you try and feed like a whole bunch of cat images into like a symbolic AI system and say, okay, pick out a cat, it's going to compare all the different images and stuff that you gave it, and it's going to look and it's going to try and find one that matches closely with the cat. And if it can find it, great. If it can't, it can't. But with machine learning being sub-symbolic, that means that it's almost like it's looking at the machine code level, right, of the inputs. So in a sub-symbolic environment like that machine learning really thrives in, it's looking at just raw data. It's looking at raw pixels and like on a screen. So if you're looking at like Atari, you're feeding the AI, a machine learning AI, just the raw pixels off the screen, and a reward that you're feeding it to tell it whether it's doing something good or bad. And so it's not looking at like, okay, this is an idea, and if the player is over here, then do this. If there's a wall over there, because a player, a wall, those are symbolic concepts, right? They represent an idea of what something is, not what it physically is, or not what it is in its raw input form. The sub-symbolic aspect of it is really where you have to focus on, from like, if you're going to approach this from a good old-fashioned AI, which is kind of like what I'm trying to do, you have to approach it from a raw sub-symbolic thing, because that's where the magic happens. That's where machine learning is taken off, because you're going a lot more hands off and just letting the computer learn whatever it needs to learn and do whatever it needs to do to be able to figure things out. And if you try and do that on a symbolic level, you're going to fail, because symbols always are abstractions of sub-symbolic data. And so if you are just feeding it symbols, then there's a level of complexity there that just fails. Whereas if you're feeding it just sub-symbolic data, that opens up the door to anything, because you're giving it just the raw data for it to play with.
Yeah, it was a lot there, so I want to try to wrap my mind around that with summarizing, and you can tell me whether I'm on track or not.
Yeah,
So
absolutely.
if you kind of like think about our understanding of reality, we get like a lot of like sensory input, like vision, sound, all these sort of things. We get a ton of raw data in, and then in our minds, we kind of build up a hierarchy of abstractions to things that are like concise and meaningful. Now, when we try to program things in symbolic AI, we're starting at that top point that's already been constructed, trying to break that back down to the base reality we're seeing again, and then also build that back up again into a way that's useful, that the computer understands. This is obviously very convoluted. Like we've already built up something in our heads which might be flawed. Breaking it down and building it, like, why not just start at the base and build up from there, and just teach the AI just that process, so it can be a lot more direct in understanding reality, how it is, rather than just our interpretation.
Yeah. Yeah, good summary.
With that in mind, let's talk about AIRIS. What is it?
So, Iris is a system that I created. I started working on this back around 2015, 2016. And it was the idea that, it was basically that concept that I had way back when in 2004 of what if we had a computer system that could learn the rules of its environment independent from a programmer. And I was like, okay, so how can we do that? How can we do that taking at it from an approach of this sub-symbolic approach that machine learning has latched onto and ran with? And it's like, okay, if we have a sub-symbolic inputs, just raw pixel data that's going into like um, a good old-fashioned AI system, how's it going to be able to figure out what all these inputs are, what do they mean, how and what's relevant? I was came at it as kind of like if I was sitting at a new game, something that I never played before, and I was playing around and trying to figure out, okay, how do I figure out the controls? When I figure out the controls, what parts of the environment are important, what parts don't matter, like, the background or whatever, like, what is my goal? What am I doing? All that kind of stuff. And I'm thinking, okay, when I'm doing that, I'm creating like basically like a rule set in my head for like of causality. When I'm thinking about how to do something in an environment, I'm thinking about it on and planning things on a causality type basis, Okay, I'm here. I need to get over there. How do I get over there? Well, I can move my little character over here by pushing right on the controller, and then there's a wall but it's low enough I can jump up with the button, and it's all just cause and effect stuff, right? And I was like, okay, so how can I work with that? How can I build something that's based on causality? So that's what Iris is. It's an attempt to build a causality based system that converts or interprets sub-symbolic raw inputs and forms causal rules about how these sub-symbolic inputs change or affect each other or don't affect each other. And then from this rules, can we then run another algorithm on top of that, like a search algorithm or something, to build out a world model of its environment, to imagine, okay, if I'm in this state and I want to be over there, what actions do I have to do? And imagine out the actions that I have to do and then follow through with those actions. So that's the idea behind Iris.
Start with one basic building block of that. When you mentioned it learns rules. What's an example of a kind of rule that Iris might learn?
In my project, I've worked with a little, grid world puzzle game. We machine learning people, we love grid worlds because they're easy to work with. It's easy to narrow down exactly what's going on, right? So, like, take a grid world puzzle game or something like that.
Yeah,
And
could you describe what a grid world is really quick?
yes, absolutely. So, a grid world is basically you have a two-dimensional grid of so many spaces, right? You have like a 10 by 10, right? So you have 10 little grid squares by 10 little grid squares. And inside that grid space, you have something that's going on. Usually in a grid world game, it's, you have a little character that takes up one of the grid spaces, and you have other things in the environment like walls or obstacles or stuff that take up other spaces in this grid space. And the movement of the character inside this grid space is like two-dimensional. It's only, it can move up, down, left, right, or maybe it can move diagonally depending on the type of grid world or whatever. And so it's a very, very, very simple environment, right? Even like Atari games are more complex than a grid world environment, but it's just a simple little environment to test reinforcement learning algorithms to see if they can understand these very simple environments and how to interact with these very simple environments to achieve whatever goal you wanted to achieve.
Okay, yeah. So apologies for the interruption, but yeah. So
Oh,
earlier
all
talking
good.
about example of a rule that that a Iris agent might learn.
From scratch, right? When there's nothing going on and you just dump this AI directly into a grid world and it doesn't know anything about what it can do. Let's say you give it 4 actions, up, down, left, right, and it doesn't know what anything does. So it can't make any plans. It can't plan to do anything. So it has to try something. So it pushes one of its little buttons on its controller, if you will, and let's say it pushes up and it moves up. Well, what it's looking at is that in this grid world environment, there's a couple of spaces that changed from one time step to the next after it pushed the up button, right? The character changed into an empty space, and the empty space above the character changed into a character. And so it's like, okay, so those two values change when I push the up button, right? And it might, and for starters, that's very broad. Like it has a lot of things that it can think about. Like, okay, is it just those two? Like just those two pixels? Does any other pixels change or any other of the grid environment change? I don't know. And so it might press the up button again and say, okay, well now that character disappeared and the empty space above it turned into the character again. Okay, now I can narrow this down and say, okay, so here's a rule, right? If there's an empty space above the character, above this character pixel, like because it doesn't have that kind of symbolic idea of what these things are. It's just noticing what pixels change. So if this grid space, if there's an empty space above this grid space, and we push up, then that value in that grid space will turn into an empty space, and that empty space will turn into that value. That's like an example of one of the simple rules that this thing can come up with. And from these simple rules, it can build out, if it presses the other buttons and stuff, it can then understand that, okay, if I push right, then if there's an empty space next to me, or next to this character pixel, the character will move to the right. If I push left, it'll move to the left. It will see, and then it will start to see that there are other things in the environment, like walls and obstacles or objectives or whatever, you build in this grid world. Because this rule that it has, that there's an empty space next to this character pixel, this empty space, that's rule, it will start to be curious about what happens when that's not an empty space. What happens if I move or push that button and that empty space is a wall, or that empty space is a coin, or that empty space is, a green square, or whatever's in your grid world environment. That curiosity is what drives it to learn and understand new things. So if it sees something and it's building out this idea of how the world works, and it runs into something it doesn't quite understand, like it's not something it experienced before, it could be that flags that as something that it could go and learn. It doesn't necessarily have to. That's part of the planning algorithm that's on top of things, but that is something that is like a curiosity. There's knowledge to be gained from interacting in a situation where you're up against a wall, compared to the empty space.
You mentioned like the go up and the pixels change, and so it's in a different state. And I imagine that's not always going to be the case. Like if there's a wall above it, then pressing up, it it doesn't change in the same way.
Right.
So, yeah, I'm wondering like how that's represented. I think of three ideas, and then you can tell me which one is right, or if it's a combination of them. One is that it thinks it will go up, and then it doesn't, and is surprised. A second is that it sees that there's a wall here before, and it's basically in a totally new condition. Every other time there's been nothing above it, and now there is something, and so it's just as new as when it never moved at all. And a third is some kind of probability distribution where it has like some percentage chance that'll go up, and then those kind of maybe shift. So how does that uncertain or novel situations, such as going up when there's a wall and there never has been before, you may have answered this a little bit, but I'd like to reiterate, how is that represented?
So it is much like your first idea, right? It looks at a wall and it says, what's the closest thing in my knowledge, in my rules, to what I'm seeing? And if it's just starting off, the only thing it has is an empty space. So it's like, okay, it's an empty space. The empty space is going to turn into the character. There's a wall there. That wall is going to turn into the character, and it's basically just going to smash right through the wall, right? Well, so it thinks that, but at the same time, it's not confident of that, because when it's doing its calculation and figuring out, and looking through its rule sets and searching through its rule sets for what rules to apply to what situation, it calculates that it's never done this before. So it's not as confident about this interaction as it would be with something it has done before, like an empty space. And so because it has that low confidence, it will stop thinking further from that. Like it'll think, okay, I move up to the wall, I smash through the wall, and then it won't think, okay, well, now that I smashed through the wall, now I can get to, the green square that I need to get to or something like that. It will just stop in its planning because it doesn't know if that's actually what's going to happen. It has a low prediction confidence there. Now, the reason why it doesn't just like continue on and think is because it could just sit there and daydream. The less knowledge that it has about its environment, it could imagine all kinds of crazy interactions and stuff where there's like, 7 of it running around and all that kind of stuff. And so if you limit it to just stopping its further predictions when it reaches a threshold of confidence, that prevents it from doing runaway stuff like that. It sees the wall as something new. And because it's something new, that's something to explore to see what happens. And if it goes there and it moves against the wall and the pixel doesn't change because it's not smashing through the wall, well then it's like, okay, this is something new. And it creates a new rule for that, or new rules, multiple rules for that particular interaction. And so you get lots and lots and lots of rules out of a system like this.
Okay, so that actually kind of sounds like a mix of the examples that I gave. Like in the second case, like it is a new situation, doesn't really know. In the third, there is some kind of probability that's different. But at the same time, to cut off just imagining every possibility, it starts with what's closest and assumes that, but not certainly.
Mm-hmm.
Actually, there's a one minor question on this. Are there any situations where it's 100% certain of something and wrong?
Yes. In fact, that happens a lot. So in a stochastic environment, right, something where you're introducing randomness into the environment that is outside of the visibility of the AI, there's an old OpenAI gym, or I guess it's not OpenAI's anymore, but there's a gym environment problem on there. I think it's called like the ice rink or something like that, where it's a simple little grid world, but sometimes when the character is moving, they'll go a different direction than the direction that they were intending to move. And so, but that's just randomly introduced by the environment. That's not something that the AI gets to see, like when that's going to happen. And so, in situations where the AI is faced with something like that, and like Iris is faced with something like that, it will create a new rule when that happens, when it slips, and be like, okay, I slipped. Now, so this is a possibility, right? This could happen. And the next time it's in like a similar situation where it's like walking across a piece of ice or something like that, it'll be both 100% confident that it is going to continue on its way, but also 100% confident that it could slip, right? And so because of that kind of that confidence in its predictions, it's like, okay, I'm confident that I can go forward, but I'm also confident that this is slippery and I could slip. That it branches out its planning into, this is what's going to happen if I continue forward and everything's fine, and this is what I'm going to do, and if I slip, then I'll see where I'm at and continue planning from there, right? And so it kind of branches a little bit in its planning to incorporate situations where it's confident, it has the same level of confidence in with two different rules or multiple different rules, but there could be some other factor that influences it.
Okay, so yeah, it develops probabilities, but it can handle being wrong. It just creates new branches, and can
Mm-hmm.
choose between those. Uh, One thing you mentioned earlier, which am intrigued by and want to hear more about, is this concept of curiosity. That sounds like a very human kind of experience.
Yes,
I'm curious what curiosity means in the context of Iris.
right. So it's one of those things that I hesitate to call it curiosity because everybody has these concepts of curiosity and high level ideas of what this are. The technical term for what Iris has is the intrinsic subgoal. And basically, what that means is that when the Iris is trying to figure out a plan for how to get from point A to point B, and point B being, some goal that you've given it, It is going to try and make a plan, figure out a way to do that. And if it can't figure out how to do that, if there's something like if it's planning out and it just hits a wall, like mental wall, and can't figure out how to get around the obstacles in its environment, if you throw something new at it and it doesn't know what that does, right? And that's in the way of its objective, then it says, okay, I don't know how to do my primary goal. I can't do that. I can't figure out how to do that. And what it does is it falls back on this intrinsic sub goal of, okay, what are all of the things in the environment that I don't have a high confidence of my prediction for? And so like maybe this new object, I don't know what this new object is, right? I can't figure out how to get to my goal, but here's this new object. Let's go see what that does. And so it pulls the low confidence interactions out of its um, plan that it had made to try and get to the goal, and says, okay, I have a low confidence of this interaction. I'm going to go do that and learn what this is, or how this works, or how this interaction I interact with this thing. And
Okay.
sometimes that can lead to learning how to achieve its goal, and sometimes it learns that no, that's fire and that's bad. Don't mess with that.
Okay, so I can kind of imagine this as like, okay, first try to achieve the goal, and then if you can't, just try to learn more about the environment. And the way you learn about the environment is you start with the things that are the most strange and uncertain and explore those first.
Yep.
Actually, that's kind of neat because I'm imagining myself like when I was a kid, playing through games of Legend of Zelda, like that kind of would have been more or less my mental process. Was
Yep.
start with, okay, I want to get to this end boss or through this puzzle, and if I'm stuck, then like, okay, there's this weird block thing. How does this work? And just poke at it, throw
Mm-hmm.
hook shot at it, throw boomerang at it, throw
Bombs at it.
everything
Yep.
else at it, and just see how it learn as much about it as I can, and then try to piece things together. Now would probably be a good time to get a little bit of visual on this so that the audience can kind of see what we're talking about here.
So this is a version of Iris that's running right now. This is a simple puzzle game environment. It's a grid world, just like we were talking about, where the objective is that this little robot has to get all of the batteries. Once it gets all the batteries, then it can complete the level. Now, the one that we're looking at right here, this is called the Mind's Eye tool. And the Mind's Eye tool lets us see inside what the AI is doing, right? This is the plan that the AI is making. I can switch and I can look and see all the different states that the AI has thought of when it's considering how to make this plan. And you can see how it's thinking of all these different things. And sometimes it'll kind of head over this way, and then it'll head over this way, and it can kind of head up there. And then whichever state reaches the goal first, that's the one that it's like, oh, okay, that's my plan. Like, because that's the closest one that I can do. And so we can look at and see it doing its plan, and then I can tell it to go do its plan, and it'll run over there and do that. And then it'll make a plan to go to the next objective, right? And then I can tell it to do that, and it will do that, and then it'll think of what the next objective it needs and go on and do that. Now this is already a like trained iris, right? This iris has already seen all of these environments. This has already seen all of how this works, and I can show you what I mean by some of the crazy things that this system can come up with. So here's the same thing, but with a empty brained AI, right? We just dropped this fresh AI. It has no knowledge of anything. It doesn't know what to do. Its current plan is nothing. The predicted states, it's trying to predict its 4 actions, but it has nothing. Like it can't predict any of the changes to its environment. It hasn't seen what any of these actions do. And so now we can tell it to do something, and it moved up, and its current plan is still just one step. It doesn't really have a good concept of how this works yet. And I'm going to just jump for a couple forward here. And now we can see, like, okay, now it's starting to be able to make predictions about how these things work, right? How, if I move up and I move down, how do these work? But it's not really well refined yet. And you can tell because it's imagining that sometimes when it moves up or down, some of these empty spaces turn into more robots than exist. And, it's got 3 of itself in the world. And so you can see where it's easy for it, like, especially when it has limited knowledge, to just explode in its thinking of how the world works. And so we kind of stop it from doing that.
So when it's showing multiple robots on the screen, what it's kind of imagining there is, I predict that when I move up, there'll be a robot where I am currently, and also one above, and also one below. Or
Yes,
something.
exactly. Yep. And so it's kind of having to refine down these concepts of these rules of what it's seeing and how these sub-symbolic values are changing. And as it refines its concept, sometimes it explodes, right? Like, here's a perfect example of this, right? It thinks, oh, well, if I move to the left, all of a sudden every single empty space is going to turn into me. Woohoo! There's going to be a whole bunch of me. It's going to be great. These limited understandings of how the world works start to get refined as it starts to do more actions, and eventually it starts to have a better concept of, okay, I get it, this is how this works. And there's a couple times when it thinks, okay, I'm going to move against a wall and I'm going to disappear, but the wall's not, and the wall's going to stay there. And it's trying to, like, figure out, okay, here's all these different things. This is a perfect example here of showing its plan of, okay, I kind of have an idea of how things work, but I haven't moved against a battery yet. I don't know what that does. I'm curious. That's the lowest confidence that I have. I have some confidence of how moving against walls work because I've done it. It's not perfect yet, and it's not 100%, but moving against a battery is a complete unknown. I have no idea how that works. And so let's go do that. And so it does it. And as soon as it does that, it learns, oh, that's my goal. That was my objective. I just got to, the goal that I was given was to increase my score. My score value just went up. That's my objective. That's what I need to be doing. Okay, cool. And so when it sits there and it plans its next thing of what to do, so then it thinks, okay, so moving right against a battery is something I need to do because that increases my score. My score is my goal. Doesn't quite yet understand, like, its interactions when it has a score. So it has some more things that it has to experiment with to kind of refine down these ideas of interaction.
Something I just noticed there, I don't know if this is an artifact of the demonstration or what's actually happening, is like
Mhm.
it took a long time to get to that first battery and a lot of exploration. Once it got there, it just navigated directly to the second battery.
It did.
So does that
Um,
mean that it's learned navigation already?
I don't really want to say that it has learned navigation so much as these are the rules that dictate the environment. If you build out an idea of how these rules work and you think ahead of however many steps of however many steps ahead, this is what the environment's going to be. If you think that many steps out ahead, you can trace back and figure out what the sequence of actions are from your current state to whatever that action is. And the reason I say that's not really so much pathfinding is because it's not really guided. When you think about pathfinding, you're thinking of, you have directed planning. The learning part of this is learning the causal rules. That's all that it's learning. There's no, the learning, all the other stuff like the planning algorithm, the getting from point A to point B, the objectives, the goals that we give it, that runs as a separate algorithm, separate thing on top of this learning part. The learning is completely independent from the objective or the goal of the AI. And so that leaves you a lot of flexibility, like a lot of flexibility in what you can do with that, with the planning of the AI. You can have it so that you can give it a heuristic to care about that distance. Like, if you're closer, that's better.
I
Oh,
asked before, like, what do rules look like? And
yes.
you gave a good description, but I'd be interested to see like exactly what a rule looks like.
Sure. So here's an example of one. It's a 2D rule. The value that affects is 0, which is an empty space. The absolute, the ABS, that means that this is the value that this value changes into, right? So the 0 changes into a 1. And so that means the empty space turns into a robot, right? When you press down. The inclusions, this is the important part right here, right? So the inclusion is that if the value in the x is on the x coordinate is 0, and the value in the -1 coordinate in this grid world from where you're looking at. So -1 being the space above you. If the space above you is a robot, this rule is, and the space that I'm looking at is an empty space, and the space above is a robot, then this, and you push, and the action is down, then the empty space will turn into a robot, and the robot is expected to turn into an empty space from this one rule. So, like I said, a lot of this is gobbledygook, but it looks great to me because I can read it and I know what all of this means. But like,
If
here's,
someone really wanted to, they could put a wrapper on this that translate it to something
oh
else.
yeah,
If you
absolutely. Like, you can absolutely put like a better wrap around this and a better way to directly interpret this gobbledygook of rules into more visual things. It's kind of like the with that mind's eye that I have going on in the background here. You know, I can output its plan of action and all that into a text file and read that text file and figure out, what it's doing. But it's much easier if that text file is converted into something visual for us to be able to look at and see directly.
Yeah, and that's making a good interface, not a fundamental interpretability kind of thing.
Right. Yeah, exactly.
Well, I want a quick question on terms of like what the robot is seeing here. Does it see like the whole grid world? Does it just see the spaces around it?
Right.
What is it?
So yeah, it's this version sees the entire grid world, and let me, I don't have a good log for that. But it's seeing each one of these spaces is an integer, right? It's a 0, the character is a 1, a wall is a 2, a battery is a 3. These arrows are a number. I mean, it's all different numbers. And so this part on the right here is kind of like an easier on the eyes version of what it's seeing.
I noticed on your channel you had another example where it was recognizing letters.
Ah, yes, yes. MNIST, the handwritten character recognition.
So for the audience here, MNIST is a classic machine learning task where that illustrates the basic value of machine learning techniques in that it gives it a data set of a bunch of handwritten and labeled examples of characters. It trains on looking at them, and the value of it is that it generalizes some rules for what is a 7, what is a 2, what is a 3, what is a 5, and so that it can then look at new handwritten numbers that are not in its data set and be able to determine what they are. And you can actually see a direct value of this if you ever go to a bank and put in a check in there, and it's is able to read the value that's on it. Like that's a practical real world example of a machine learning technique. It's rather basic by today's standards, but when I was describing it years ago to people, that would be a go-to kind of thing. But in any case, a reason MNIST is very popular is because there's a free published by MIT and extensive data set. It's a very simple challenge, compared to other machine learning tasks. And so it's often a benchmark for new systems to see how they're able to perform.
Yep, and that's exactly what I was doing with it for my system. Was I wanted to see if this generalized to other things. It kind of works the same way as you would like a grid world environment in or an action space environment. You show it a number, and then it pushes a random button to see if that number is correct or not or whatever, and it's shown what the answer is, right? It's shown, is this a 0, is it a 5? It starts with no label, so you show it a number, you don't tell it what it is, and then in the next state you tell it what that number is. And so it's building a causal rule kind of thing where, okay, if I'm in state 7 and the action is reveal the answer, what is the next state going to be? Is it going to be a 2? Is it going to be a 7? Is it going to be a 0? Is it going to be whatever? And so it's just trying to figure out what the label is going to change into, from no label to label, and it's guessing what that label is from 0 to 9. And so it runs through, like, there's 70,000 characters total, 60,000 in the training data set, and like 10,000 in the test data set. And so I just as an experiment to see if this was if this concept went on. And this is old results, right? Like this is from like 2016, 2017. But it got like 78% on on over 2,000 images. And the reason it was only running it in 2,000 images and not the full data set is at the time of this video, the 2016, 2017, this entire project was being coded in GameMaker. Like this was not it wasn't done in Python. It wasn't done in any kind of modern programming language. This was being built in a video game engine. And so it ran terribly. It ran very, very slow. And some of the things that I was doing back then helped contribute to that slowness. So I could really only do about 2,000 images before it bogged down to the point where it would take like a month of just sitting there to be able to process all the way through. I've done more since then. And after converting everything over to Python, it now gets like a 98% accuracy rating. So a couple of things that I have tested Iris on since converting over to Python, but not recently, is of course the MNIST and also cartpole, which is a classic control problem. Just making sure that that what I was building was not limited to grid world puzzle games.
And what's the objective of cartpole right here, just so people know?
Yeah, so the objective of cartpole is that it starts in a random spot with a random angle on this little pole. And the goal of cartpole is to move the cart in such a way that the pole stays vertical and remains vertical and doesn't tip over. So, if you shove it too far one way, it'll fall over. If you shove it too far the other way, it'll fall over. The whole thing is just keeping this pole upright by moving that little block at the bottom.
Is the pole controlled by some kind of physics that will make it fall over if it's tilted?
Yeah, it's physics based.
How much special code and engineering did you have to perform to generalize it? Or what had to change when you're moving it between these different environments?
It's basically just what data is getting fed to the AI.
Were there any special challenges you're working in this kind of continuous space, given in a rule-based structure? Oh, and for the environment, when I say continuous, that means there's like the grid worlds. There's like a limited number of actions and movements that you can make. You could express as like 1, 2, 3, 4, and so on. Whereas continuous, it can be anything in between.
The solution was to break that into reasonable, to basically round it up. And I found that rounding up to 3 spaces was too many rules, and rounding it up to 2 spaces was just right. Narrowing down the continuous space into kind of like discrete chunks is really the way that the system was able to handle these continuous spaces.
What are your long-term goals with Iris? Like, what do you hope to do with this?
Robots. I mean, that's really what my goal is that bring home that childhood imagination of having like a Star Wars droid like R2-D2 to hang out with. That's the long-term goal of this project. Is reinforcement learning is a system that is designed for planning and action planning and solving problems. And that is what I want Iris to be able to contribute to, is having a system that can learn how to create plans to solve problems. And I think that, right now on the development timeline of where Iris is, being very nascent, little grid world puzzle, the next step is more complex environments, right? Atari is my next goal. If I can get it to play Atari games, then it will have scaled up in a reasonable way to a more complex environment. And from there, I can start doing more of the interesting things that I want to be able to extract out of its knowledge to see if it understands. does it have, is it able to create a sort of a theory of mind of the other characters that are in the environment? Like if you're playing a Pac-Man game, you can build up a prediction of how the ghosts are going to behave by observing them, right? You're watching them move around, and the top expert Pac-Man players have got that nailed down. They know, okay, if the ghost is over here and I'm down here, it's going to come down this way, and they know the patterns of movements and patterns of behavior. They have a theory of mind of the Pac-Man ghosts. And I want to see if Iris can create, and not only create, but I can extract out that theory of mind from of the other game characters from these more complex environments.
How far you expect this approach to be able to scale? One specific challenge with this that I'm kind of imagining here is that as the environments get more complex and you have more different types of inputs and outputs, all of these interact with each other. Which suggests to me that there'd be kind of a polynomial like expansion or or exponential increase in the number of rules needed to navigate increasingly large environments. And you can get some of that with better processing, put more computer power at it, and that
Yeah.
seems like it would solve it if it was like a linear increase.
Mm-hmm.
But whenever you
It's
have an
like,
exponential,
yeah.
then like no matter what linear benefits you throw at it, whatever like little bits of tree pruning you throw in,
Mm-hmm.
exponentials are hard to fight unless you turn them into something linear.
Yes.
So is that a problem? And if so, is that something that you see a path towards or dealing with, or just where do you stand?
Yes. Yes, exactly. And that is absolutely a problem in like the raw subsymbolic aspect of this, right? If I was looking at a computer screen or like a TV screen, right? Or like a 3D environment where like say I'm in Minecraft and I'm the character and I see the whole world around me and I turn to the left and the whole screen shifts, right? And at the subsymbolic level of just the raw pixel data, that's intractable. There's no way to be able to calculate all of that and apply all of those rules. You need a massive Google data centers to even come close, or some kind of supercomputer.
Mhm.
The key is going to be is taking that subsymbolic data and building abstract symbols out of it, pulling and extracting instead of looking at all of the pixels of this tree and doing each one on an individual basis, abstract out the concept of a tree. And the tree is going to move to the right. So this blob of pixels is all going to just shift over and calculate all of that as just one big blob instead of individual pixels. And these individual concepts, extracting out all of these individual concepts of what these things are to figure it out. And so abstracting out that level is, taking these sub-symbolic concepts and turning them into kind of like symbolic ideas, but just not hard coded by us, but hard coded or but extracted out from the system itself. Taking and then manipulating and planning around those symbolic concepts and figuring out all these different things on a higher level, like a higher abstraction level. And so the higher level you abstract, the easier the computation is because the simpler the environment is.
So I just summarizing the problem here, is actually kind of takes us full circle back to what we were talking about at the beginning, is that like you can't start on the symbolic level because you're going to be missing things, programming in your own assumptions. You just can't get all of the relevant details without something getting lost. So you need to go down to the sub-symbolic level and get all the raw data. But once you're getting past the trivially simple environments and getting to something more complex, eventually you have to bring the symbolic back, and
Mm-hmm.
as a way of shrinking rules down to something that's a lot more manageable, rather than, so for example, rather than looking at every pixel on the screen, you're having concepts like trees and creeper, or ground, or whatever else. And that has to be done by the system itself. If that's programmed in directly, then you're back in that first problem.
Yep, exactly.
Now, I'm aware that machine learning approaches have some of that built in, kind of as a surprising side effect in a way with the deep learning. So the earlier layers of neurons are probably just finding like really basic sub-level components, and interpretability, like the little bit of findings in that seem to bear this out. So like the early neurons, like things like might see something like this as a line. Later levels of neurons put together some of those concepts from the earlier layers. And so by having multiple layers, you're able to go from the subsymbolic to the symbolic, or climb up levels of abstraction, thus getting both the starting at the lowest level of detail and then also working up to something more manageable, which is my understanding of why they're so powerful.
Yeah.
So do you have any ideas for creating some kind of analog to this levels of abstraction within IRIS?
The rough idea right now, because it doesn't work in complex environments, so I haven't really been able to experiment and develop on this. But the rough idea of what I have right now is to group things into commonalities, right? So like as in like a more complex, like an Atari game, right? You have a character, and that character is not made up of one pixel; they're made up of multiple pixels, and multiple pixels in a certain arrangement. And so when you move, or when you press an action or whatever, those pixels change and move across the screen, and they move together as a group. And so the idea is that when, just like when we're looking at things on the very detailed, fine, granular, subsymbolic level of this pixel changed and this pixel changed, so there's a rule, that we create another rule that says, okay, all of these pixels have changed. They've all changed. And so what if all of these pixels are there, and if all of these pixels are there and we move right, then all of these pixels change. And so we start to group together and categorize these different things that are changing, and different things that are happening, and the different changes that are happening at the same time. And so we start to if we can categorize these sub-symbolic rules into more categorized symbolic rules at like some level of abstraction, then we can say, then instead of saying if I move right, then this pixel changes, and this pixel changes, and this pixel changes, and this pixel changes. They say if we move right, then these pixels all change. It's just one big group. We can just apply that change to those pixels and have the expected outcome, rather than doing it on an individual pixel level. And so that's the first level of abstraction, of figuring out, what things are grouped together, what things are related to each other, what inputs are related to each other. And then from there, possibly extracting out further concepts of things, like, okay, so this group and this group, there's an AI, the character and an enemy. And so here's these two concepts. And if the character is, facing if the enemy is in the same row as the character, then the enemy is going to move towards the character, right? So then we have these two things. We have a symbol of a character, a symbol of an enemy, and we create this behavioral rule abstraction of, okay, if the player is over here, and if the enemy's here, the enemy is going to move towards the player because it's facing the player. And so these are higher level abstractions, and these are that's an approach to doing this that I'm taking. But I don't know if that's going to be effective or not. I haven't got that far.
Right. That's understandable. You're one person working on this, and what you have is actually very impressive.
Oh, thank you.
As it is. I like the idea, like, and it's also this early on, it kind of makes sense to be as vague as things like finding groupings, especially because this is just my own intuition here, but it kind of seems to me that whatever's going to work as a solution is going to need to have some level of recursiveness to it. Otherwise, that knowledge engineering, putting your own assumptions in, kind of can very easily sneak in through the back door. And that's again one of the values of machine learning is that it's just neurons again and again, all the way through using that same process. If you could get something analogous, I can imagine that is like not just a next version, but as a next generation of this. But I can see like an inherent value that we were talking about at the beginning of there being some like interpretability by default, being able to run plans without them actually executing, so to make it very like predictable as to what it does. And so even if it generates some rules that have some nasty side effects, like at least we'll be able to know those in advance and be able to cut those off, and we'll be able to change it a little bit more directly. So that seems very relevant to alignment if it's able to scale. But what about like some more modest kind of things? Like two that I'm imagining. One is maybe there are certain concepts in it that could be used to replace especially icky parts of the machine learning paradigm, or maybe like narrow applications that are especially high risk. But other I'm thinking of, which you may be able to answer freeform a little more easily, is just applications, possibly in game design, that you could use something like Iris is just like more or less as it is, with maybe just like a few tweaks.
As far as like the machine learning thing goes, and like this project's translatability into other fields and stuff. Most important concept, as far as from interpretability and AI safety and stuff, is disconnecting the predictive part of it, figuring out the learn that it learns, just the interactions that are going on in the environment, and it's separating out what those actions are, or how those actions are, what goals, the objectives, all that stuff is completely separate from the learning. If you could train a neural network to only make a prediction, to have it be able to produce and take an input of a state and produce an output of a future state, just one step ahead, just one state ahead, based off of what action it's going to do, then that's something that you could replicate the concepts of what Iris is doing in a neural network fashion, because there's no neural networks going on in Iris at all. It's a lot like good old-fashioned AI, right? It's a lot like symbolic AI. If you could do something like that with a neural network, then you could have those same kind of functionality, and maybe even more effectively. And as far as what Iris can do in like game development, for example, yeah, that's something that I've kind of thought about doing a couple of times, is starting a game project and building like the ideas that I have with Iris into that game, and see, and that kind of stuff. So I think it translates really well in a game development type way. I just don't have enough time to make a game on top of making the AI on top of working a day job. So
From a game development perspective, there's this trade-off in game design between like effectiveness and just making it fun. And
right.
often what makes a game fun is when it's sort of predictable, or when it's like flawed in interesting ways that the player can then take advantage of. You see it actually a lot more clearly in like Legend of Zelda boss fights, for example. Like you're fighting something that's mechanical. It follows a process. It's
Yep.
adaptive to an extent, but really it's kind of just teaching you
Following a
how to defeat
pattern.
it,
Yeah.
because its goal is really to teach you a mechanic, not to just be an enemy, because that's
Right.
ultimately what makes things fun. Now, the relationship to the alignment topic is that to some extent it matters how things are done. It's not just get to the goal, but like we actually to some extent care how we get there. So being able to exert that control is useful, but not 100%. Sometimes you just want to have a thing that figures it out. So I'd be kind of just curious what kind of game context where an AI that finds the solution through exploration would be optimal. I'm sure they're there. It's just it might be something not obvious.
Well, I think from a game development perspective, I think that having companion AIs, like, you wouldn't necessarily want it as an enemy because it would kick your butt. But
Sure.
having it as a companion would be awesome. Like, take Minecraft, right? People play Minecraft and they have Minecraft and love playing in multiplayer environments and stuff. And it's like, okay, imagine if you had an AI agent that could operate in a Minecraft environment, but it was, and it was like your friend. And you could interact with it, and it would do its thing, and it would wander off, and it would collect stuff, get resources, and maybe build some houses and stuff like that. And that, you know, it doesn't have to get super complicated. Like, it doesn't have to have super complex goals or super complex plans. And you could even like pre-program some things into it, like, a design for a house. Like, instead of just say build a house, you have a design, like a subset of designs for a house. And then it's like, okay, here's a bunch of designs, pick one in the code, and it picks a random house design. It's like, okay, what do I need for that? I need oak, and I need brick, and I need, some fire. So I'm going to need a flint and steel. And, it plans out from there, like, oh, okay, these are the resources I need to get. And then it wanders off and goes and gets those resources. And so it's just kind of an interesting character to have in a world that you're also in, like a friendly NPC character type thing, or interactive NPC character. And I think that's primarily where this thing would be interesting, is like as an interactive NPC, not necessarily, maybe as an enemy, but not necessarily as an enemy, maybe as a friend, or maybe just as an indifferent NPC that's just in the world doing something. And it's just kind of fun to watch it, run off into a cave and get chased by a creeper and get blown up while it's trying to build its little house, or something like that. Something to make the worlds a little more lifelike.
I would love to see a Iris controlled companion in Minecraft. That sounds pretty awesome. Anyone watching this, sees your demonstration of Iris and sees like, oh, this is really awesome. I want to work on this or something similar. What do you have to say to anyone with that kind of interest?
Well, you can check out the project website is iris-ai.com. I'm sure we'll have a link in the description. Or if you want to reach out to me directly and talk about this project or other ideas around this project, feel free to do so. You can reach me at my email, which is berickcook@gmail.com. I'm on Discord as Berick Cook. It's a nice thing about having a unique name. It's easy to get that handle. I'm on Twitter at Berick Cook. I guess it's X now. And
It's still Twitter.
so, yeah, it is. It really is. So yeah, feel free to reach out, connect with me. We can talk some more about it, or you can just follow along on my YouTube channel, which is also at that website, iris-ai.com.
Thank you very much, Berick, for your time. This has been really interesting, and
Thank you, Will.
yeah, appreciate it. So good luck on your continued development.
Thank you.